All right, so we all know that a cryptographic hash is great for telling us if a file's been messed with, right? That's data integrity. But, and this is a big but, that's only half the story. How do you actually prove who sent that file in the first place? Well, let's get into it. And that right there is the big question we're tackling. Think about it. Let's say you get an invoice and it's got a valid hash. Awesome, you know the numbers haven't been fudged on the way to you. But how do you really know it came from your actual supplier? What's stopping an attacker from just creating their own fake invoice and calculating a new, perfectly valid hash for it? That's the problem. That's the authenticity gap. So, what's the answer? Well, it's actually pretty clever. We take the public, everyday process of hashing, and we add just one secret ingredient, a private, shared secret. And that secret is what turns a simple integrity check into a powerful authentication tool. Okay, so before we get to the solution, let's really dig into the problem. Why exactly is a standard hash function all by itself not good enough when you absolutely have to know who the sender is? And this really lays it all out, doesn't it? On the one hand, you've got what a hash is great at, integrity. You change even a single bit in that data, and boom, the hash completely changes. But, and here's the massive catch, the algorithm to make that hash, it's public knowledge. So anyone, and I mean anyone, including a bad guy, can just whip up a fake message and generate a perfectly valid hash to go with it. So sure, the hash proves the message is intact, but it proves absolutely nothing about who actually sent it. And this is where the hero of our story comes in, the Message Authentication Code, or as everyone calls it, a MAC. This is how we finally add that missing piece of the puzzle, that layer of trust. So what exactly is a MAC? You can think of it like a special security tag that you attach to your message. But this isn't just any tag. It's generated in a very specific way that proves two things at the same time. One, the message hasn't been touched. And two, it could only have been created by someone who knows a particular secret. See? It gives you both integrity and authenticity. The whole package. And here's the core idea in a nutshell. A MAC isn't just a simple hash of the message. No way. It's what you get when you combine the message with a secret key, a key that only the sender and the receiver know about. That key, that's the magic ingredient. Without it, you simply cannot produce the correct MAC. It's like a secret handshake for your data. Now, out in the wild, you're almost always going to run into a specific kind of MAC called an HMAC. That stands for Hash-Based Message Authentication Code. We don't need to get into the nitty-gritty of the formula, but what you do need to know is that it's the standard, battle-tested way to build a secure MAC using hash functions you've already heard of, like SHA-256. It's basically the industry workhorse for this stuff. All right, so we get what a MAC is conceptually, but how does it actually work in practice? How does it build that bridge of trust between two people? The whole process is actually really straightforward. So, first things first, and this is the most important part, the sender and receiver have to have a shared secret key already. That's step one. Then, the sender takes their message, uses that secret key to cook up a MAC, and then sends both the message and the MAC over to the receiver. Okay, so now the receiver has the message and the sender's MAC. What do? Well, they run the exact same calculation. They take the message they got, use their copy of the secret key, and generate their own MAC. And now for the moment of truth. Do the two MACs match? If they do, bingo. The receiver knows for sure that the message is legit, it's unchanged, and it came from the only other person on the planet who knows that secret. Okay, but wait a minute. This is a great question, and it's probably what you're thinking right now. If an attacker intercepts the message and the MAC, what's to stop them from just changing the message to something evil and then calculating a new correct MAC for their fake message? I mean, they have the message, right? And the answer is so simple but so powerful. They can't. They just can't do it. Sure, an attacker can modify the message all they want. They can even run a hash on it. But they are missing the one thing they need to create the correct MAC, that shared secret key. Without it, any MAC they try to create will be a dud. It won't match, and the receiver's check will fail instantly. That secret key is the entire defense. Now, you've probably also heard of something called a digital signature, right? They also give you authenticity and integrity, so you might be wondering, well, how is that different from a MAC? And that's a great question, because the difference is actually really, really important. This chart really spells it out. The biggest difference comes down to the kind of keys they use. MACs use what's called symmetric keys. That means one shared secret that both people have. Digital signatures, on the other hand, use asymmetric keys. That's a public key that everyone can see and a private key that only the sender has. Because they're simpler, MACs are way faster. They're perfect when the two parties already know and trust each other. Digital signatures are a bit slower, but they solve a totally different problem, proving your identity to the whole world, to anyone, even complete strangers, because they can just use your public key to check your signature. And look, this isn't just some abstract computer science theory. MACs are a critical part of modern digital security. They're working behind the scenes all the time in stuff you use every single day. I mean, they're literally everywhere. When two servers talk to each other using an API, they're using MACs. That little lock icon in your web browser that says your connection is secure? Yep, MACs are helping to protect that data. Secure messaging apps, payment systems, they all rely on MACs to make sure messages and money are coming from the right place and haven't been messed with. So let's just do a super quick recap of the big takeaways here. Number 1, MACs give you the 1-2 punch of both integrity and authenticity. Number 2, the whole magic trick works by combining a public process, hashing, with a private shared secret key. And finally, number 3, MACs are the absolute go-to for secure communication between two parties who already trust each other. Which of course leaves us with one last massive question, doesn't it? The entire security of this whole system hinges on that shared secret key. If an attacker ever gets their hands on it, it's game over. So how in the world do two people securely share that secret in the first place, especially over the public internet where anyone could be listening? Well, that's a fantastic question, and it's the topic for our next explainer. Thanks for joining me.